Today I'm going to be Phil Hopkins. Well, Phil tried to convince me to give his talk for a third time, but because he thought it would be a better delivery with a French accent. But I think it's not going to work. So I'm going to talk about some of my own work. Once again, it's actually good that I was swapped with Phil, because Joel introduced nicely what I'm going to talk about here. And this is work I've been doing. It's preliminary as well. This is work I've been doing with, in collaboration with Devriendt Liz in Oxford and my former PhD student, Tae-Sun Kim, now postdoc in Princeton. And Tae-Sun is going to be looking for a job. So watch him. He's a real star. All right. So the outlook of my talk is, so I'm going to talk about the impact of turbulent star formation, and turbulent should be in quote here in this title, and you'll see why in a minute, on high redshift galaxy properties. And so the outlook of my talk is going to be fairly simple. I'm going to present the problem. I'm going to try to make the case for why we should worry about turbulence in the simulations. And then I'm going to talk about the modeling efforts that have been done to take that into account. And finally, I'll discuss the results, the recent results we've obtained, and the impact that this has on the galaxy properties at higher redshift. All right, so what is the question? The question is simple, is simply, how should we form stars in these cosmological simulations, right? So should we be using the observed star formation surface gas density relation? This is the standard Koenig plot. And what I want to say here is basically this law that is measured, that this surface density of star formation rate proportional to gas surface density to the power 1.5, is this simply Schmidt law with a given efficiency, right? Or is it telling us something more complicated? And I would argue that, you know, this is average on kiloparsec scale. So as long as in your simulations you have a resolution of kiloparsec, it's probably fine to use that. However, if you go to high resolution simulations, such as Joel was mentioning, and you have 10 parsec resolution, you should in principle be able to resolve the structures of disk or galaxies. And so you should worry of whether this is actually the way you should implement star formation. Okay? And so if you answer the question positively, that this is how you should do star formation, then generally what people do is a 2-parameter implementation of that. So basically, you only form stars above a certain, when the density of gas goes above a certain threshold in the simulation. So this threshold actually depends on the resolution of the simulation, right? The better resolution you have, the higher this threshold is going to be. And Joel has argued nicely that you need to go to a very high threshold star formation to get realistic galaxies. I think this is not enough, and we'll come back to that in a minute. And so basically, you could argue that you need to at least reach an average molecular cloud density like 50 or 100 atoms per cc for this threshold to be realistic for star formation. And then you apply this simple Schmidt law with an efficiency of about 1%. So what you are assuming, in effect, is that this star formation efficiency, so the amount of stars that you form per free-fall time, is a universal parameter. All right? Now I'm a theorist, and to me this is deeply unsatisfying, right? Because I think I'm including some of the physics that's relevant for galaxy formation, right? And if that's the case, this efficiency for star formation should be a prediction from my simulations, right? This 1% should come out, whether it's, you know, whether it's driven by turbulence, feedback, or whatever. If I'm including these processes, then this 1% should come out. All right, so this is deeply unsatisfying, but, you know, it needs to be done. So why would you need to reach, let me just briefly mention, why would you need to reach average molecular cloud densities? Well, you can look at these nice observations here of gas and star formation in different tracers. And what you see, if you look at the, oh, there's a pointer here. That's the laser pointer. That one should work if I can figure it out. Yeah. So if you look at traces for recent star formation, here is dust emission, here is H alpha, and you see that this seems to correlate way better with the molecular gas traced here by CO emission than the atomic gas. Okay. So hence the claim that you need to reach at least high densities for the threshold in order to get realistic star formation in galaxies. Here is another way to do it. It's same surface density of stars versus gas density. Here the gas density is split in H1 and H2, and you see that the correlation is actually much better with H2 than it is with H1. Okay, so, and I've told you that this were observations average on kiloparsec scale. So actually this is taken from paper by Mark, where he has actually plotted in red here symbols the Milky Way clouds, and what you see is that this epsilon, this efficiency for star formation in molecular clouds seems to be also very low. Okay, now this is not average on kiloparsec scale anymore. This is average on cloud scale, so I would say hundreds of parsec scales. But in this high resolution simulations that we have now with 10 parsec, we actually at least for the most massive clouds, we actually partially resolve them. All right? And so the big caveat in this is even if you look at molecular clouds, so that's observations of the Perseus molecular cloud, the scale is given here by Heiderman et al. What you see, this is a molecular cloud, what you see is that stars do not form everywhere in the molecular cloud. So even if you reach this high densities of molecular cloud, star formation does not happen everywhere. Here, what you should see, what you should look at is the yellow and red objects, which are stars which have not yet migrated outside of the regions where they were formed. Okay, so when you see that they cluster nicely, they don't form all across the cloud. In other words, I would claim that molecular cloud, reaching average densities of molecular cloud is a necessary condition, but it's not sufficient. All right? And so basically, essentially, this is a difference between forming stars with a low efficiency everywhere in the cloud or versus high efficiency in dense cores only. And here is a paper by Phil where he actually compared several star formation recipe that you can use in isolated galaxies and mergers. And basically, I focused here on 3. That's the density threshold criteria that I'm talking about. Here is an isolated disk, right? Here is, in this column, is the same star formation recipes, but for merger. Okay, and so there is the density formation threshold here. This is an attempt of forming stars where there are molecules, so the molecular tracer thingy, and this is another criteria that we'll come back to in detail, where you actually form stars in regions which are self-gravitating. Okay. And what you see here is the star formation rate as a function of time. For these 3 things, it's dark blue, light blue, and purple. And you see that the star formation history for the Milky Way type galaxy are not very different. Okay, and also for the high redshift merger, it's not very different. However, in details, where you form the stars differs vastly. So another way to look at this is these curves, which show the density weighted distributions for star formation rate for the different star formation prescriptions. Just focus on the top 3. And what you see, essentially, it's where you are forming stars. What is the density of the gas where you are forming the stars in the simulation? And you'll see that this self-gravity criterion that I will come back to later forms stars I would claim in the proper way, in the sense that you mainly form stars in the highest density region to your simulation. Your density threshold here is very interesting, because the density threshold here is 100 atoms per cc, and what you realize that you're forming all your stars at the density threshold of your simulation, or most of them. Okay, And so here's the same plot for the merger, which is even more dramatic in the case of the self-gravity, because the peak at the threshold of molecular clouds here, average density of molecular clouds, is greatly suppressed. And so the molecular criterion here forms stars even at a lower density. It peaks at even a lower density than the simple density threshold. So what's the missing ingredient? Well, turbulence is the missing ingredient, I would argue. So here is a beautiful picture of CO emission in the torus molecular cloud. What you see is so basically you see the CO intensity in different velocity bands. The blue ones are coming towards you, green ones is about abreast, and red ones are going away from you. And what you see, that's the scale here, and what you see is that you see a big mess. You see turbulence. There's no doubt about it. And so there's evidence for that the interstellar medium and molecular clouds are supersonically turbulent has been known for a while. Here is the standard Larson relations, which basically relates the size of the molecular cloud to the line width size. And if it was incompressible turbulence, the exponent here, they would be a third. Okay? And what you see is that since that gas we know is at about 10 Kelvin, right? The sound speed is here. So all these clouds are very supersonically turbulent velocities. Okay? So, and at some point, if you draw a vertical line here, you can see where you transition from supersonic turbulence to subsonic turbulence, and that happens on scales which are about 0.1 parsec. So we don't resolve these scales, okay? Even with the highest resolution cosmological simulations that we have today, we don't resolve those scales. So we are in the supersonically turbulent regime, okay? Now, what does this have to do with star formation? Well, it has been argued that the stars actually form in regions where this transition to subsonic turbulence has occurred. Here is a fantastic observation by Pineda et al. of the Perseus molecular cloud. And what you see here is the region. So basically what they did is that they measured the fine structure NH3 lines. And what you see is that in the region where you're actually forming a protostar, you see that the velocity dispersion is low enough that you can actually separate the two components. And as you move away along this direction and you enter the supersonically turbulent dominated regime, this line becomes broader and then goes away. All right. And so this has been, so basically, and so stars form in the region where turbulence has dissipated enough in the cloud that it's dominated by thermal motions. Okay, so that's the claim. Now, the problem is what drives this turbulence. So here is a simulation. So you can think it's been driven by internal processes. Here is a simulation by Wang et al. That actually shows you how you can drive a messy turbulent region with jets, outflows, radiation from stars. But the problem with this is that we also know that in non-star forming molecular cloud like the Polaris, we have a beautiful observation that show that this cloud is turbulent. There's not a single star in this cloud, right? So, so basically, turbulence has to have a source that is also external, okay? And so essentially, this is good news for us because we should be able to capture at least that turbulence, even if we don't know how to do feedback properly, okay? And so here's an example of an isolated simulation by Tasker and Tan, which was then revisited by Van Loo later. So he did a resimulation of this region, and you see when you increase the resolution, what happens is that you get more and more structure in this cloud. So you're pumping the energy from the galactic shear and the cloud motion to actually drive the internal turbulence of these clouds. Okay. So, okay, I've talked about turbulence. So how can we use that? How can we use this thing to the properties of the turbulence to make our star formation better in the numerical simulations? So essentially, you do it through the probability the density probability function. So here is the quiet region in the Polaris flare. Again, that's observations. And you can measure the probability density distribution of the gas there. There's no stars, remember. So before any stars form, all right? And so it turns out that this is a log normal, okay? This is the log normal probability density. And so it's characterized by S, which is just the ratio of the density of the gas to the average density, okay? And the width, okay? So what is the question then is what is the width of this probability distribution? Well, the width is actually driven by two things. Turbulence, but it actually depends on exactly what turbulence is doing the driving. So here are simulations by Christoph Federoth and collaborators where they simulate a box, an individual cloud as a box, right? And they force the turbulence in that box. So they impose velocity power spectrum of fluctuations on large scales. And there's essentially two ways you can do that. Either using a solenoidal forcing, where the curl of the velocity field is zero, or compressive forcing, where the divergence of the velocity field is zero, or compressive forcing where the curl is zero. And this is a map of the Coulomb density, and you see that it looks very, very different in these two things. And so what you do then, you just measure the PDF of the gas, right, in the simulations, okay? And what you see is that the width of this PDF not only depends on, because these are done with the same amount of turbulence, so the same RMS velocity fluctuations. You see that the width depends on whether you're in the compressive mode or the solenoidal mode, okay? So essentially, what you can show from the simulations is that the sigma s, the velocity, the width of this distribution depends on the forcing, whether it's solenoidal or compressive, and the Mach number, so the amount of the RMS velocity fluctuation that you have. All right? So when you've done that, you're almost done, because then you can use the PDF to derive the star formation efficiency. What you do is that you just simply integrate from the critical transition of the sonic regime, which scales like that, and then now you have a prediction for the star formation efficiency in the free-fall time, which depends on the forcing, on the Mach number, and on this parameter, which is simply it's called the virial parameter, which is simply twice the kinetic energy divided by the gravitational energy. So all these, I would claim, you can measure from your numerical simulation. Okay. All right. There's a little bit of dust under the carpet in the sense that this model actually predicts the dense core mass function and not the stellar initial mass function. So basically, there is a little epsilon factor here, which should be of order unity, that is still there. Okay, and so here is a way to see it. These are observations from Alves et al. From the trapezium cluster. This is the observed IMF. This is the observed dense core mass function. And what you see is that the dense core mass function has the same shape as the IMF if you just shift the gray line by about a factor 4 or so. Okay, so that's what this dashed line is just simply the gray line shifted there by a factor 4 or so. So it means that this epsilon parameter is like 25, 50%. So essentially, if you could plot it as a 3D plot, that's the star formation efficiency, right, as a function of the Mach number and the virial parameter. If you assume a mixture of solenoidal and compressible modes of 0.44, which is very close to what's observed, and I'll come back to that, is very close to what you measure in simulations as well. Okay, and what you see is that you have wild variations depending on whether the cloud is bound, so alpha v inferior to 1 or not. You have tremendous variation in the star formation efficiency. Okay, so I should add that this model, this analytic model, is an excellent description of the star formation rate or the dense core star formation rate that's measured in high resolution simulations. And when I say high resolution, it's AU simulation resolution of supersonic driven supersonic turbulence. Here is an example for that from Padoan and Nordlund. And so basically, if you fit this model that I've just described from Federoth and Kless to the simulation, that's a game they played, you find reduced chi-square of unity in the terms of the star formation efficiency that you predict. So let me come back to how we should form stars in simulations. Well, you should get rid of the resolution dependent density threshold, and then just form stars if your velocity dispersion, so that's the turbulence part, plus the sound speed squared, is inferior to the gravity that it's bringing the gas together. Okay, so essentially this is a self-gravity criterion if you set beta equals 1, or you could see it as a turbulent Jeans length criterion to pick the loci of star formation. In a sense, what we're saying here is that if gas is gravitationally unstable, there's nothing that will prevent it from forming stars. And so what we do is we form a star here, and we use the same law, but now the epsilon, the star formation efficiency, is this function from the Federoth and Kless model. Okay. And what I would say is that when you do that, you're being self-consistent, because these simulations by Federoth and Kless, from which they derive their model, contains exactly the same physics that you put in the cosmological simulation. There's no difference. So in a sense, if we had AU resolution, if we were able to reach AU resolution, and turbulence was driven in the simulations, we would get the same star formation efficiency they would. So we're just using the results to extrapolate our star formation. Okay, so how wrong is this that the clouds are self-gravitating, so with alpha with variable parameters less than 1? Yes. How wrong is this? Well, here are observations, local observation by Kaufman et al. It's a compilation of all these observations. It's a measure of the variable parameters as a function of the mass of the cloud. And what you see immediately is that the very massive clouds, those that we can resolve in a cosmological simulations, I would claim above 10 to the 4 and above 10 to the 4 solar masses, they all more or less, for the vast majority of them, they have variable parameters less than 2. So they all gravitationally bound. Okay? So here, let me come to the parts of the results. I'm like trailing by a lot of time, but so what we did is that we set up a series of simulations that we call Nut. That's the name in Egyptian. That's the Egyptian goddess of the night, of the sky. That's where the French word nuit comes from. And since we were using Ramses, we kept up with the Egyptian theme. And so essentially, it's an AMR simulation, so it's identical initial conditions with a dark matter particle mass of 5×10 to the 4 solar masses, halo of 5×10 to the 11 solar masses, redshift 0. And what we did is that we included different star formation, this different star formation recipe, and also 2 different type 2 supernova feedback implementations. I don't have the time to go into the details of this. I would just say briefly that the first one is that we used the Dubois and Tessier 2008 formalism, and we just put a set of solution after a 10 megayear time delay in our simulations. And then we compare that to the Kim and Chen prescription, which self-consistently check whether or not we are able to capture this phase, in which case this energy conserving phase, in which case the same model is used. Otherwise, we use a momentum conserving phase. And here's a resolution study available in the Kim and Chen paper that shows you that if you basically have enough resolution, these two things converge to the same answer. All right, so how does it look like? So that's the galaxy we're going to be focusing on right here. Here is the turbulent star formation model, and what I've done to show you what the difference between the star formation recipe to illustrate it here is that in blue are the contours where we go above the isodensity contours in a slice of the simulation through the disk, where we are above 100 atoms per cc, and in green are the gravitationally unstable regions prescription. So what you end up doing, you see here, is that you are forming stars in the turbulent or the gravitationally unstable regions only with very high efficiency, only in some places in this molecular clouds. So does it make a difference? Do we care? So I'm going to compare here. I'm going to try to convince you that it does. We compare 3 simulations with a density threshold prescription with no feedback, the energy-conserving supernova feedback, the momentum-conserving supernova feedback, and then the same 3 simulations with the same 3 prescriptions for feedback, i.e. no feedback, energy-conserving, momentum-conserving, but just changing the prescription for star formation. So how does the galaxy look for this different prescriptions, right? Here is the standard density threshold. So the density threshold here is 400 atoms per cc. Okay. So here is no feedback, energy conserving feedback, momentum conserving feedback. Here is the same with the turbulent star formation prescription, no feedback, energy conserving, momentum conserving. Okay. And you see that it looks very, so that's the gas density, all right? Seen face on. That's H-on. Right? So you see the first one, the no feedback with the density threshold, is a razor thin disk, which flares at some point, right? And then you start adding the feedback, so that's the inefficient energy conserving feedback, as the very efficient momentum conserving feedback. Here's the disk with no feedback in the turbulent prescription, energy conserving, and momentum conserving. All right, so let's go a little bit, now that I've shown you what they look like, let me just go into a little bit more into the quantitative details of it. So here are phase diagrams. So that's mass weighted, that's the temperature versus density in all these runs. And essentially what you see is that, of course, and so these lines are constant Jeans length. These ones are constant pressure. And the resolution of our simulation is corresponds to Jeans length of 10 parsec. The thermal Jeans length is here. Okay, and so if you have no feedback, of course, the cooling stops at around 10 to the 4K or so because you have no metals. If you have metals and you have different star formation recipe, you see that the phase diagrams are completely, massively different. It's just because the metals are getting mixed much, much more. So now, just let me briefly convince you that that we're in the supersonically turbulent regime. Here is, so I'm going to skip on this velocity dispersion plot, but as the phase diagrams, this is the log of the Mach number. And so a Mach number of unity is here, this line here, okay? And so what you see is that in dense regions, in all simulations, but particularly for the ones where the cooling can go very low, you are at Mach numbers of order 10. So we are in the supersonic turbulent regime. We are dominated by supersonically turbulence. Here is the measure between the mix of compressible and solid orbital energy. And you remember I'll use this B parameter of 0.44 in my recipe for the efficiency of star formation. Well, here's 0.5. That's all the runs. It's pretty close to 0.5. Compressible, the ratio, that's the ratio of compressible energy to solid orbital energy. All right, results. Galaxy star formation rate. Well, it's a mess for all these runs, so let's take them 2 by 2. No feedback runs. What you see is that the histories are of the stellar mass at z equals 3 are comparable about the universal baryon fraction. If you start including feedback, that's the energy feedback runs, you actually do nothing if you have a density formation threshold. You actually reduce by less than a factor 2 the amount of stars that you form if you are turbulent star formation. If you go to the momentum feedback runs, you're able to reduce by a factor 2 in the density threshold, but you actually reduce by a factor 7 in the turbulent star formation run. And the most interesting maybe is the galaxy rotation curve. So here, what you see as solid lines is the circular velocity. So basically a measure of the mass, if you want. So of all the components, dark matter, stars, and gas in the simulation, it's superimposed in the symbols is the gas rotational velocity. And what you see, the color coding is the same. I haven't gone through that, but in blue and gray are the runs without feedback. Okay? So if you don't have feedback and you have a high star formation density threshold, you have this enormous peak of velocity, of rotational velocity. And this gets worse as you increase the resolution of your simulation. You get higher and higher peak. We've done simulations with 0.5 parsec resolution, and this peak goes above 1,000 kilometers a second. Right? If you now simply use a turbulent star formation recipe that I've described to you, without putting any feedback, you get the gray curve. And lo and behold, the peak is gone. Right? And so you can easily understand that in the sense that if you have a density threshold, the center of your galaxy, the gas at the center of the galaxy is always going to be above the threshold, because that's where you have the highest gas density. And you're always going to form stars, even if you form them slowly. You're always going to form stars. You're going to pile up stars. You get a very dense stellar core that forms, and this is not going to go away. It's going to be very difficult to destroy it. In the turbulent star formation run, what happens is that, yes, you still have this very high density of gas in the center, but you also have very, very strong velocity dispersion. So you suppress star formation in the center, and so you suppress this peak. Okay? And this is completely degenerate with feedback. Here in blue is the threshold for star formation with the momentum feedback prescription. Lo and behold, this core is gone as well. Okay? So let me just flash up my conclusion and just say that it's good news that we finally entered an era where we now have enough numerical resolution to resolve the turbulent ISM in cosmological zoom simulations. And here the scale that's important is the scale height of the gas disk, because that's what's setting the scale of your clouds. Okay? And the bad news, in my opinion, is that we need to revisit the subgrid models that we've been using to take advantage of this extra resolution. Right? And in particular, we have to pay attention to how we form stars in the simulation. And then I hope I've convinced you that turbulence-driven star formation alone has potentially non-trivial consequences for the dynamics of central regions of galaxy, and that when it's coupled to feedback, these changes actually can become dramatic. Even with a simple model, which we just have a standard set-off solution for supernova, we can reduce the mass of stars that we form within a factor 3 more than what we do with the density threshold star formation. That's it.
Yeah. I'm a little worried about how reliable your results are given the resolution you've achieved. There's a reason that people like Christoph and Paolo do 4096 cube simulations, and that's because even at 4096 cube, you sort of don't quite believe the product, the structure of the turbulence, because you're only barely resolving the inertial rate.
Yeah.
You're not resolving it at all.
No.
So, given that, are you able to actually say anything meaningful about things like the Vero parameter, the compressive to solenoidal ratio, the Mach number, or is that entirely dominated by numerical dissipation?
Well, that's a very good question, of course. So the claim that our claim is that what we are resolving is actually the large scale. So we're not. What we're doing is that we're saying, okay, we resolve whatever turbulence there is on the 10 or 100 parsec scales, we have an idea, we get an order of magnitude of what we have in the simulations, and then we plug in onto the subgrid model of Christoph. So essentially what you would, their box, their 4096 cube box, is the one cell in our simulation. So we measure the global quantities and we use their results to actually predict what star formation efficiency we should have, right? That's right. That's right. That's a worry. But you know, as the resolution gets better, what we've done is that we've tried. I haven't shown the results here because it's preliminary. But what we've tried is that we've tried upping the resolution of the simulations. Right. So we've gone from 10 parsec. We have simulations at 5 parsec, simulations at 2.5 parsec, and when we measure on the 10 parsec scales the values for this velocity dispersion, okay, they vary, but not by much. So, you know, that's the best we can do.
Julien,
yes?
what disrupts molecular clouds in your simulations? Is it supernova energy? In the momentum feedback runs, yes, that is. Yes. Yeah, that's right. But you know, that cannot be right.
Well, and also, what I should say...
I mean, in real universe, that doesn't happen. Molecular clouds are disrupted well before supernova even start to shoot, right?
No, sorry, I should correct that. No, it's not that, because we have this 10 megayear time delay before the supernova explodes, right? Yes. So these clouds are also changing on whatever resolution we have during these 10 megayears, right?
So what disrupts molecular clouds before supernova starts to?
Nothing. Right? I mean, turbulence. Whatever it is.
Destroys them because
no, it just changes the properties.
So it's supernova energy which disrupts molecular cloud.
Well,
one way or another, right?
That's all we put in there. So if they are destroyed.
Probably said that, and I missed it, but in the run through the turbulent model, when you form stars, you do so at 100% efficiency.
Well, no. So that's what Phil does in his recipe. He takes an epsilon equals to 1. What we do is more complicated than that. We use the efficiency that's predicted by Federath and Klassen, right? So we use this. That's the value for epsilon, which is their model, which is given by this complicated thing, right? So we measure the variable parameter, the Mach number in the simulations, and we assume B equals 0.44, and then from this chart you can read what the star formation efficiency is. So we have a spatially dependent star formation efficiency.
And have you checked what that produces globally?
Yeah, so that's what I was very fast on this because, you know, I mistimed myself pretty bad. But you can check what it does on.
You're eating literally in our coffee break.
Oh, sorry. All right. That's the difference between the two runs in the star formation rate, and that's the mass of stars that you form.
No,
this is
the efficiency, the epsilon of 1%.
Yeah. So the gray one is that the efficient. Well, all the numbers are very high. Essentially, we form only stars where alpha is one or smaller than that. So the efficiency is very high. It's always, you know, anywhere between 10% and 50%. Right? It's not 100%, but it's close to it.
But it's very close.
Yeah.
Okay.
All right.